Hello, everyone. This lesson, we are going to look at a neat application of net force that we looked at in the previous lesson, and how it explains buoyancy, how things float, why things float. And then we're going to go on to look at the relationship between force and acceleration, which is really what Newton's law is. So we'll end up learning about Newton's law and see how to use it. Okay. I left a question in here that's the solution worked out for one of the vector addition questions. So the question 30 in the previous lesson assignment had a force of 6 newtons up and a force of something else, whatever it was, like 30 newtons at 35 degrees and so on. It's probably said like north 35 degrees east, and it was 60 newtons north. Those two forces both pulling on the same object add up tip to tail, resulting in a combined vector, right? A net force like that. Okay, so you calculate the values by just getting all the components added up, and end up with the total components, and then you get the size of it based on the normal stuff, right? Doing the component, adding up the components. So the x component total and the y component total end up being the red. Normally it might show it on a separate diagram to make it less cluttered, but I think that works. All right, so don't forget about the idea of vector addition. Not really doing it by scale diagrams anymore because we know about the math answers or math way of doing it. Okay, obviously more precise and less work and so on. So again, review from yesterday, our last lesson. If this balloon has a constant velocity up, then there's some things we should know about it. So constant velocity up means that it has a net force of 0. So therefore, F net equals 0. And so there's no net force on this thing at all. The free body diagram would look like this. Now we know there is a lift force up, and then that would be balanced by that gravity force down. So I'm actually just going to draw it right on there and then show it like that. So we know they're the same size because of how I just drew it, right? So F G, let's just say, and you certainly can still have vector arrows on there and that, but the end of the world if they were left out because it's pretty obvious, right? So if you look at F net equals F lift plus Fg, we know that this is 0, right? So we have 0 equals F lift plus Fg. And so really we get that the lift force is equal to the negative of the gravity force when we do the subtraction from both sides, right? So if what I did there wasn't intuitively obvious, this kind of proves that it's true as well, right? So F lift equals that negative Fg value. All right. Here we have two forces obviously going on. We have the force of the one group this way and the force of the other group the other way. And again, same kind of analysis, right? We know that acceleration is 0. And so that means the net force is 0. So you can think of it as F1 plus F2. And so same idea here, right? We could just say that's equal to 0. And so if we subtract one of them from both sides, we'll have they're equal to the opposites of each other. Kind of analysis that just makes sense here. So on. Okay. Hopefully that is easy enough to picture. Last time I did this, I included the gravity forces as well, which you could as well here talk about the gravity force that's on the people and the force of the ground up, right? So gravity Fg and Fn, if you will. We're going to learn more about that Fn later on, normal force, but the balancing forces, I forgot to mention it this time, but so that should be good. This video, I'll let you just click on it and watch it yourself. I'm just pulling things from it. It's kind of neat. It's neat enough. It's it's a hot tub filled with sand, and then the person blows air up through the sand, and it makes it act kind of like a fluid. I'm actually using the diagrams that he did for the analysis to do with the forces on the object, right? So picture the air flowing upwards and the gravity down. If those are balanced, and this thing's going to kind of float, right? Now, in the description in the video, they did a really good job of showing how buoyancy works, and so I just thought I'd show that. So the deeper you are in water, we know there's more pressure. If you've ever dove down in water, of course, most people have, right, where you feel that pressure on you. What's happening is the deeper you go, the amount of pressure, water pressure on you is really equivalent to all that water that's like above you, like it's on top of your head, you know. Same thing with air pressure, actually. Air pressure is because of all of the air that is above you, kind of sitting on you, right? So this is the picture you'd have, really, right? Air pressure or water pressure. The deeper you go, the more pressure there is, and it's just pressing everywhere all the time, right? So if you look at all those arrows, what's the net force? Well, all of the sideways ones just cancel out completely. And then the vertical ones, you have a bunch of big arrows up and a bunch of little arrows down, right? And so the overall result is the buoyancy force, right? You get a little bit of, you get an upward force and an upward force and so on from each of the pairs of the vertical ones. So if you picture, what color would work here? Maybe green. I don't know. Yeah, that works nicely, right? For each one of these, you have a corresponding force of a little bit down, right? Can't see those much right now, but when I move them out of the way here, you're going to be able to see each one of those, right? Means we have this much of a force up as a result of those. And so those add up to the buoyancy force, right? So that is this thing, the buoyancy force. So if the F net from pressure is greater than gravity on an object, right? So that's just I shouldn't have said F net, it's the F total, I guess, in this case, right? F net's kind of a special name for the result of all of the forces, right? So this is the total force upwards due to the pressure gradient. If all of those forces are greater than the gravity force, then it actually gets a lift force up and it accelerates up. Or if they end up the same, it just stays where it is and floats and so on. Okay, so if you put a toy down in the water, it comes accelerating up because the buoyancy force is greater than the gravity force on it. If F net is less, then it sinks, right? So looking at objects like that. And so, if you look at a rubber ball, like a dodgeball or like a basketball or something, whatever, a rubber ball of some sort, in comparison to a helium balloon, if they're the same size and shape, which one has the greater buoyancy force? It's a bit of a trick question because this one floats, this one falls, right? But the actual buoyancy force would be the same. But the difference is the amount of gravity force that's on it, really, right? Because if they're the same shape, they're going to have that same pressure difference upwards, right? So don't be tricked by the size about the size of the force based on the effect, right? You have to consider all the forces in order to be able to judge all the information. So this is just procedure tips for the activity. So let's look at the end result, the idea of it. So we're going to have, I'm going to show actually my video first for this. So it's basically an experiment where we're going to look at the relationship between, go back up here. Here it is here. So the relationship between force and acceleration that I mentioned earlier at the agenda portion there. So in person, I get students to design and carry out, but the design's pretty scripted because I need to show how to use the equipment, right? But basically you can push and pull on the force sensor, and then it has an acceleration sensor too. So really you're gathering pairs of numbers, force and corresponding acceleration. And you just get it to graph it, and then you're looking at the results, okay? So this is what that ends up looking like. Go here. So you can see the graph ready to go here. There's the cart. And my hand is going to come in here and actually move that thing back and forth. Okay? And so that's the plot of all of the forces and accelerations. These forces are forward, accelerations forward as a result. These are for forces backwards when I was pushing and pulling on it. See that nice, really nice straight line, right? Well, obviously that's representing a linear relationship. And so I go ahead and I highlight that, get a nice line of best fit. And then that line of best fit has a slope of 0.739. Or 739 really, if you're looking at the factor that we're used to. But basically you look at that result, you think, okay, what would that be? So right now we're looking at a proportionality constant between force and acceleration. We're looking at the relationship, the physical quantity, if you will, that is the connection between how much force is on an object and how much it accelerates by. And so I think it's pretty intuitive that that would be mass, right? If you push on a heavy mass, it doesn't accelerate as much as if you push on a lighter mass. So more force, more acceleration. The relationship is really the connecting relationship concept is the mass. And so if we look at that result, go ahead here in the video, we have that 7.739, that's in grams. So put it in kilograms, sorry. If you put it in terms of grams that this scale measures, it's 739, and then experimentally we see the result is 755.7. Okay, so very much in the same ballpark, 739 or almost 740 to 755. If you do the error analysis on that, we have a predicted mass, or based on the experiment slope of the relationship is 739. Measured mass is the 755.7. Is this a percent deviation or a percent difference situation? Well, this is what it should be, right? This is what it should be. And so we're looking at how much it deviated from what it should be, right? And so percent deviation would be the choice. And so you'd say, okay, well, you're going to do the 755.7, take away the 739, divided by that 755 that it's supposed to. So how far are we off in comparison to the size of what we're trying to measure, right? And so then you end up with, like, I think that's 16.7 divided by 755.7 times 100%. It ends up being around 2% error, which is pretty darn good for a quick little experiment that really is designed to determine or illustrate or help you understand the connection between force and acceleration, and that it's mass, and really that is Newton's law, right? Newton's second law. So the idea of how this becomes Newton's second law is in this page here. So either we can just notice the idea and recognize that mass is a concept, or we get the slope and see that it is mass experimentally, right? So basically, we're getting the idea that force over mass is acceleration. That's the other way around. So really, I'm looking at, here's y equals mx plus b. We've got force equals mass times the acceleration. So we're getting this formula, F equals ma, right? Because just using the fact that it's a linear relationship from the result. Okay, so the y equals mx plus b information from grade 9 literally leads to Newton's second law, which is F equals ma. So that's just basically a little neat experiment to do in person. Certainly it's neat. And then to see that it works as a video, it's, pretty neat equipment, I guess, right? But a neat way of exploring that relationship rather than just thinking of it as another math equation. So this relationship of force, mass, and acceleration, so we're talking about the net force on an object is equal to the mass times the resulting acceleration. We don't always write in net. Sometimes people get lazy and just say F equals ma. Just be aware. Units, of course, are in newtons, or if you notice, the units for newtons would be kilograms times meters per second squared. And that's literally what a newton really is. Okay. So that's why the earlier on I changed the point decimal 7 or whatever is 5 number, or 755 number to be 755 because we're converting to kilograms to grams and so on. The wordy version of this obviously is, if there's a net force on an object, it will accelerate in the direction of the net force at a rate proportional to the mass and the force. Okay? So if you push on something, it accelerates, in other words, right? So this is similar to what we looked at before, where we looked at if you have constant velocity, you have a net force of 0. Just now it's more specific. It's not just a net force of 0. You can have net forces of any number along with an acceleration that pairs up with it. So, obviously if you're given, say, the mass and the acceleration, you could easily calculate what the net force must have been. Or if you're given the net force and the mass, you'd be able to calculate what the corresponding acceleration would be. So the main idea is there's this, ultimate connection between net force and acceleration, right? But really, we're going to use F net equals ma to do this. So given any two of the numbers, you can calculate the third. I only looked at being given net force and mass, get the acceleration, and kind of the vice versa because of the connection I'm trying to establish between acceleration and net force. So pretty easy stuff, right? Where you look at a question like this and you say, okay, well, I'm given the mass. So given mass equals 7 kilograms and a net force of 2 newtons, and I'm asked for the acceleration. And so you look at this and you analyze this, and so here's our given and our required, and now we're analyzing and saying, hey, I've got an equation to do with this, F net equals ma. And so I've got 2 equals 7 times a, and I can just divide both sides by 7 and end up with the answer for the acceleration, right? Even though it's not a nice number to look at or think of in your head or whatever, it's easy enough to calculate. So 2 divided by 7 gives you 0.2857. So if we had 2 significant digits or 3 significant digits or whatever, you just round appropriately, right? So 0.29 or whatever. If this was 7.0, this was 2.0, then we use 2 significant digits, in which case we'd be doing 0.29. So given any 2, you can solve for the third one easily enough with this kind of an equation. It's your typical 3-variable equation. Give you 2, solve for the other, solve for the third one. Here we have given the acceleration 4 meters per second squared. Same object as before. I was like, we don't have a number. We have a mass of 7 kilograms still. And we're looking for the net force. It's at the same mass, right? The object was later seen. So of course we have F equals ma again, or F net equals ma. And we have F net equals the 7, the mass, times the acceleration, giving us this net force of 28 newtons by multiplying. And in each case here, obviously, therefore, acceleration is, therefore the net force is, and so on. Okay, and then there's the third version. If I gave you the acceleration and mass, the net force and the acceleration, I guess, and you'd solve for the mass. Okay, I'm not including one of those, but obviously it's very doable. And so this idea of there being a net force and there being acceleration can be seen in diagrams as well. And so this free body diagram here for net force not 0. So this Plymouth Roadrunner dragster here obviously has a nice large applied force forward and presumably a much smaller friction force backwards. And so it has a net force forward and an acceleration forward, right? So if we're looking at this and we said, okay, F net equals the FA plus the FF. Just going to try and carry this out here. Plus FF, color coding here. So if these were numbers, let's say this was, say, I don't know, 100 newtons, and then this was maybe minus 10, or 10 newtons, but the other way, of course, right? So I can just show it as 10. Then you can see that you'd have this listed in here as a 100, and the other one as a minus 10 for putting the direction system in at that point numerically, right? So on the diagram, the arrow pointed to the opposite direction, so it was obvious that it was opposite. Anyway, so we end up with the net force being 90, right? And this is, you can tell the direction system here, the way it was set up was to the left was positive, right? So we have a net force to the left, we have an acceleration to the left, and so on. But yeah, the main idea is just the free body diagram to do with it. And obviously we could have had a gravity force and a normal force, balancing out as well, because it's pretty obvious that thing's not accelerating vertically. Okay, so same kind of thing here. We have a fairly large applied force forward and balanced by some amount of friction backwards. And if we're just looking at the free body diagram, that could be it, right? The Challenger space shuttle is obviously accelerating up at that point. So let's just point that out. And so we have the acceleration is up. So we have an applied force up, and then a gravity force that's fighting that, but it looks like it's still accelerating up, right? So we have that was supposed to be FA, and we have some gravity force down, and so we have a net force up in each case, right? So you can tell there's a F net in that way, there's a F net this way, and the sizes would be determined by the vectors and so on. Note that the net force is not on the free body diagram, right? F net is not on the free body diagram, right? F net equals the result of adding up all of the forces on the free body diagram. Okay, so that's something that really needs to be reminded later on in circular motion stuff. But right now, even you shouldn't list that net force, of course. So what about this one? So acceleration due to gravity. Okay, so what are the forces that are on these objects? So this gymnast here, what forces are on the gymnast? Well, really, there's just a force of gravity. Could talk about air resistance and things like that, right? But the person's clearly not moving fast enough to have air resistance be a major factor. So there's just the gravity force. Here we're looking for the free body diagram on the ball, okay? On the ball itself. So question is, what's the force of the girl on the ball? And a lot of students say there's the force of the kick. And be like, wait a minute, look at the instant this picture was taken, right? Unless the girl is using the force, there isn't a force, right? This is zero unless they're using the force, if you will. And so really the force of gravity is the only thing that's on this thing as well. And it's causing it to accelerate due to gravity. It's causing it to fall down. Think of our projectile motion lesson, right? The object is in projectile motion, free fall type motion. And so it's acceleration in the vertical directions due to that gravity force. In the vertical direction, everything else is not accelerating. And same thing here, right? So we have a force of gravity, and that's it on those guys. Right? That's the only force that's on those objects. It's just the force of gravity. I'll put that one on there too, since the other ones ended up on the diagrams themselves. All right, so that's it. When you're looking through this, these guys are the three types. So just straightforward, just write the given and the equation and the numbers in and solve it. And then the other questions here. This one we talk about. Oh, look at that. Hang on a sec. All right, so this question here is really just about the equation itself. F equals ma. And so the idea is they're saying if the force is doubled, what happens to the acceleration, right? And if the mass is halved, so just take the equation, you look at if this was made to be half as much as what it was, what would happen to the acceleration and so on. Okay, so that should make sense if you think of it that way. These guys are easy enough here. You can tell obviously there'd be the net force. You could even just take away that amount from it and show like that's the net force. And so what motion would this have? Well, it would have acceleration in that direction, right? So each of those have that kind of flavor to it. And then down here, if we have this is the first one where you actually have to get like, I'll just give you the tip here, right? Where you have to realize that you have F net equals the two forces added up. And so you've got a force and you've got a force, get the net force and then get the acceleration. Calculate the acceleration if we have those forces on it. So that's really just an F net equals ma once you've determined the net force. And yeah, this part B is optional for you to do if you want. It's really just now you have an acceleration and you have a, initial velocity and a time, to calculate how far it went. That's just a review question from the previous unit. All right, so hopefully that makes sense. I like to say that a lot. Yeah, if you have any questions. Bye for now.